building a compiler framework specifically for accelerator programming, GPU programming basically. And the focus of today's talk is our IR, which we're calling C-lisp, and a macro preprocessor that we wrote for it. But before that, I'll explain a little bit about why we're doing what we're doing, because it is still a new project. So starting off, this is the state of affairs in the current GPU compiler ecosystem. It's fragmented. You can see that, unlike in the CPU space where you have something like LLVM supports almost any backend that you would want. And so to implement any front end, you just need to compile to LLVM. But with GPUs, it's more like you have separate tool chains for separate backends. And in cases like for NVIDIA GPUs, critical parts of these tool chains are closed source, which is another problem we're trying to deal with. Now, Now, there are projects like MLIR, SICL, and stuff, but we have problems with each of these. So MLIR, we just find difficult to work with. I guess this is a bit of a controversial statement to make, but MLIR kind of locks you into C++, which is one of our problems with it. And there are other problems which I'll come to later. SICL is a set of abstractions built on top of C++ that basically abstract out the aspects of GPU programming in a device-independent manner. And there are compilers for SICL that do really well, like adaptive CPP. But the biggest problem with all of these is generating C++ code is difficult, at least in our opinion. So optimized kernels have traditionally been handwritten, but if you want to programmatically generate optimized kernels, it's not very easy to do it in C++. So that's the main problem we're trying to solve with Llama.lisp. The name is still a work in progress. So yeah, this is the approach we take to constructing the framework. Like MLIR, I guess we adopt a multi-layered approach. And one of the points of discussion today is our IRs, which are formulated entirely as expressions, which we believe makes it easy to generate code in these IR languages. So first, a primer on S expressions for those of you who don't know. An S expression is basically either a token, that could be a string, a symbol, it could be a number, or it's a list, each element of which is, again, an S expression. So, and the first element of an S expression list is typically an action word. So for arithmetic, you can have add AB, which means A plus B. The table is there. And another point of interest for this talk is that we use JSON as an exchange format for S expressions, because the S expressions, that is lists and basic token types, are a subset of the JSON schema. But JSON is much easier to work with in most programming languages, which is why there's an equivalence between S expression and JSON. So we just use JSON as an exchange format. There's a small syntax error. There should be commas over there. Now, a step further with S expressions, you can use S expressions to represent abstract syntax trees. So rather than, you extend the idea of an action word, and you say the first element in an S expression list is a node type, and the arguments and the rest of the elements of the list are children of that node. So if you can see the declaration statement in C, this is a declaration statement, which is why the root node is variable declaration. And then you have var, and the name of the variable, and the type of the variable, which is a integer pointer. Now, when you put that into S expression, you've got declare, which is the action word, var is one argument, and this entire thing is a second argument. Recursively, the first argument in the right subtree is peta, which means it's a pointer type. So this is the idea on which our IR layer is built. This is how C-lisp code looks. On the left, you have a simple C function that implements fused multiplication and addition. And on the right, you have an equivalent implementation in C-lisp. So the first thing you'll notice is that before that, to put it simply, C-lisp is basically C semantics in an S expression format. That's basically what we tried to do. We didn't want to reinvent the wheel and come up with our own semantics. So you'll notice that both programs have the same structure. You've got functions at the top level hierarchy. Within functions, you've got statements, and some statements can be expressions. And of course, the expression operands can be expressions themselves. So, I've tried to align up the lines. Now, another thing you'll notice about C-lisp is that it's very minimal. This is on purpose because we wanted to, one of the things about using LLVM IR is that the IR is insanely huge. There are a lot of features and only a small subset of it is what we'll be using and what we'll need. So we tried to, so C-lisp eventually compiles down to LLVM IR. We basically chose a critical subset of LLVM IR and exposed that functionality through C-lisp expressions. Which is why you'll see that although C allows you to have an initialization value for a variable declaration, you cannot do that in C-lisp. Now, the consequence of this is that there's usually only one way to write one feasible way in which to write a C-lisp program. But at the same time, this does not come at a performance cost. Okay, I don't have a picture of it, but we did run a test wherein we compiled C-lisp code using our compiler and an equivalent C code using Clang with -01 optimization, and they performed equally. So at the moment, we've gotten a language that is as performant as C and that can present equivalent programs. So like I said, C-lisp is very minimal. It's difficult. It can be difficult to work with because of that, which is why we saw the need for a powerful macro system. Because we want to keep the core of the C-lisp language small and easy to maintain, easy to extend, whatever. But at the same time, there are always features to be had. So, which is why we decided to create a macro preprocessor for C-lisp. So on the left, I've put that's basically a diff, just to show you what kinds of substitutions are possible with pre-lisp. And on the right, you've got the definitions for these macros. The definitions are in Python. That's the important thing about pre-lisp. The fact that you can, most macro systems right now either use the language itself as the macro definition language, like Scheme and other Lisp family members, or they have a very small restricted language created for the purpose of that macro system, like it is in C. But here, we decided to use Python because it gives you an insane amount of flexibility in writing macros. On the face of it, it may not work out so well, but what makes it feasible is, again, the fact that we're using S expressions. You'll see that none of the macro definitions on the right make any sort of API calls in order to do their code gen. And their results are all entirely native Python data structures. I'll go into a couple of examples now about pre-lisp macros. So I had to indent these JSON expressions like Lisp S expressions because I was running out of space. But yeah, macro expressions are denoted using the comma or unquote, which is again borrowed from the Lisp family. Here you've got unquote and a single token as the unquoted expression. So pre-Lisp recognizes that as the macro expression, searches for a variable by the name EOF in the macro module, in the module in which your macros are defined, searches for a variable by that name, substitutes it back into the source program, and you get this as your result. Now, since our parser is written in Guile scheme, the parser from S expression to JSON is written in Guile scheme, which is why you see comma EOF being translated to unquote EOF. That's just a minor detail. But yeah, this is how simple substitution works. This is, I guess, analogous to hash define name value. Now, next up, you've got parametric substitution, or function-like macros in C, wherein you've got the unquoted expression being a list, or in some sense a function call. So pre-Lisp searches for a callable by the name of INCR in the macro module and passes the arguments var and 45 to it. And the macro returns an expression of this form, which is, substituted in the same way. Now you've also got splicing substitutions. In both of the first two examples, you see one macro expression being replaced by another expression, a single expression. Splicing allows you to replace one expression with multiple. So you denote it using comma at, again, unquote splicing from the Lisp family. This is a parametric macro like the previous example. This is an implementation of, you would have seen in the first example that I had to declare and then initialize. I couldn't do both of them in a single step. This macro implements that. You have an expression of this form, and it gets expanded into this. Now, as a proof of concept, we used this macro system to implement signature inclusion from C headers. So since we're working on a compiler framework for GPUs, we wanted one of the tests we wrote was a vector addition kernel to be run on an NVIDIA GPU. So we needed to make calls to the CUDA driver API. So we essentially implemented an FFI system, a bindings generation system in Python, and we were able to call into it from the C-lisp program itself using pre-Lisp. So I'll just outline how the binding generation process works. So you've got, so essentially we needed the signatures, we needed function definitions and struct definitions from a CUDA header file in order to make calls into the CUDA API, because since we're using LLVM, we already have ABI compatibility with C. So calling into C libraries is just a matter of getting the right signatures. Now, parsing C is a difficult task, so we kind of offloaded that to Clang. The only problem with which is the Clang parser will only preserve definitions of structures and functions that are actually used in the program. If you include an entire header file, and then if you have a program with just a hash include directive and you compile it with Clang, you'll get nothing in the LLVM IR. So, which is why I wrote a Python script that basically generates a program of this form. You can see that this is essentially how we're using every function or struct that we need. You've got one pin for struct tm and another pin for the function ask time. So we have a Python script that generates a C program of this form. Use Clang to compile it to LLVM IR, and we extract the JSON in the ASD in JSON form, which I believe is for debugging purposes. And from the LLVM IR module, we extract our function and struct definitions, and from the JSON ASD, we extract the fields of the names of the struct fields and type defs. And with that, we were able to achieve something like this. So we just, again, hash include CUDA.h, specify the functions that we want, that's this, and specify a type def that we want, that's cufunction. And just like that, we were able to make calls into the CUDA driver API. So I think this validates what pre-Lisp can do for you, and the entire advantage of using S expressions for an IR language. That's it. Any question?
Thank you, Vedant. Very interesting work.
So where does OpenCL and Vulkan APIs fit into kind of providing uniform interface to all of these accelerators with respect to your work?
Where do they come in?
Yeah.
So if I'm right, OpenCL basically provides libraries that you can call into that implement some standard functions. So those essentially form the, okay, for any GPU programming model, you've got two components. You've got a language and a compiler for writing kernels, and then you have a runtime library into which you can make calls. So what we've worked on so far is the kernel compilation bit, and where platforms like OpenCL would come in are when we use these kernels to, I mean, when we need standard library functions, we'd call into those libraries from our kernels. Like,
People write kernels in OpenCL, isn't it, directly?
I'm not really sure.
More questions?
So you said Python for preprocessor is flexible, but then like using the language itself as the macro language has been successful for literally every Lisp, right? So why do you think Python specifically helps in your case? Because the macro language being the same as the normal language is what makes Lisp powerful.
Right. So, like I said, we tried to build C-lisp so that it's a very, very minimal language. We're intending it to be an IR. We don't really intend for humans to write programs in C-lisp. What we eventually want is a higher level abstraction that basically generates kernels in C-lisp from a naive algorithm. That's essentially what we're visualizing. So C-lisp is not really a good language to program in as a human, which is why Python is a good macro language.
Understood. Thanks.
Thank you.